Okay, Assalamualaikum and good morning, everyone.
Morning, doctor.
Okay, so I just want to let you know that I have uploaded your assignment or project. So since last week, so for those who still don't know about this, so you can start doing the project and assignment. Okay, so the submission is at the end of week 14. So 20th June, Monday. So the assignment is doesn't involve any programming. So just using manual calculation. So try to do it, and you can discuss among you guys. Okay. All right. So let's continue with our lecture. So today we are going to learn about conservation laws. So basically, all that we have learned so far, which is about deformation and how to determine the stresses in the body, all of this will be governed by conservation laws. So you might encounter conservation laws in a lot of previous courses, like in static dynamics, fluid mechanics, heat transfer. So in continuum mechanics also, will implement conservation laws in order to make sure that the stress and strain are um, occurs within certain limits. Okay. So at the end of this lecture, you will be able to understand four different principles of conservation. So you have conservation of mass, linear momentum, angular momentum, and conservation of energy. But we are not going to cover the detailed theory, but we are going to cover how we can use this conservation to obtain some important results that will be used in the following lectures. Okay, so many natural phenomena can be described in terms of mathematical relationship. So these are governed by laws of physics or the principle of mechanics. So the principle of mechanics to be studied are the conservation of mass, linear momentum, angular momentum, and also energy. So these principles allow us to write mathematical relationships between quantities such as stress and strain. And the solution of this equation represent the response of the system to certain forces. So let's say if you have a ball and you provide a force on the ball, and to calculate how the force impact on the ball, we can use all of this conservation principle. Okay, so you might have encountered balance of energy, like um, when you pull something up from the ground, then you will know that the changes of energy from kinetic energy to potential energy. And then you might encounter balance of linear momentum, which is similar to second law of Newton. Okay, so second law of Newton, which is basically force equals mass times acceleration. And you might encounter conservation of mass, in which in one particular point or space, the mass entering that space equals the mass going out from that space. So the mass within that space is the same, is constant. And lastly, balance of angular momentum. Maybe you discovered this in dynamics or in statics when you have rigid body rotation, okay, rotation of rigid body that involves angular momentum. So let's look at the first conservation law, which is the conservation of mass. So basically, mass of a given system cannot be created or destroyed. So for example, the mass flow of blood entering an artery is equal to the mass flow leaving that artery, by assuming that there is no blood added or blood lost through the walls. So using this principle of mass, we can determine how the mass actually flow within a particular space. So the principle of conservation of mass states that the total mass of any part of the body does not change in any motion. So even though when you deform an object, the mass still remains the same, only the shape of that object will change. So in continuous mechanics, we can derive the conservation of mass in both spatial and material description. So here I didn't show the derivation because it is quite long. Okay, so I just show the final relationship. So here the conservation of mass in spatial description is given by this relationship. So here del rho del t, rho here is the density or the spatial density, plus del dot rho times v. So v is the velocity of that particular point. So here the equation also known as the continuity equation. So in steady state, so in steady state meaning that when the object doesn't move anymore, then we can assume that the time derivative equals 0. So we end up with this relationship only, del dot rho v. So for a constant density material, del dot v only. So rho is constant. So here rho is the density. So density is mass over volume. So the mass is constant, but the volume might change. Okay. So that's why we have spatial density, meaning that when you deform an object, maybe the volume is changed, but the mass is constant. So the density can change. So let's look at how we can apply this relationship to calculate something. Okay, before that, we have the conservation of mass in material description. So because we assume that the mass is neither created or destroyed, so the total mass of any material volume will be the same at any time instant. So the continuity equation in material description is given by rho naught, so initial density equals the Jacobian times rho, or the density at spatial, okay, spatial density. So J is the Jacobian. So the density, the initial density will depend on the Jacobian times the density at new time point. Okay, so let's say you are given a motion given by this mapping. So determine the material density as a function of x and t. So firstly, we can determine the spatial velocity. So to determine the spatial velocity, basically you find small v1 and then differentiate small x1 over time. So if you look at x1, so x1 is this relationship. So you just differentiate x1 with time. So only time is the variable, while the other constant, we assume constant. So we get negative x1 squared divided by 1 plus t x1 squared. And this is similar to negative x1, small x1 square. And then for v2 and v3, so v2, you differentiate x2 with time, and v3, x3 with time. So here there is no time in x2 and x3. So basically the velocity is 0. Okay, so that's why you get zero velocity. And then from here, you can plug in into the conservation of mass. So del rho del t equals negative del dot rho v. So we assume the mass or the density constant. So we get negative rho del dot v equals negative rho del v1 over del x1 because we only have v1. So differentiate v1 with respect to x1, small x1. So differentiate this, you get 2x1. Okay. So substitute this into this. So you get 2 rho x1. And then you can integrate this relationship. So integrate, so rearrange first rho into one side and the other, or time on the other side. So you get this. And then because x1 here, uh, you cannot differentiate this, integrate this because you don't have time here. So we write x1 in terms of time. So we take the original equation for x1. And then because there is a time here, then you can integrate. Okay. So here you integrate, you get ln p. So here you get 2 ln 1 plus tx1 plus a constant ln c. And then using initial condition, so let's say at time 0, the initial density is rho naught. So you just substitute in here. So you get ln c equals ln rho naught. And then try to simplify, you get this final answer. Okay, so the density will depend on the initial density and only x1, okay, and time. Okay, so it's fairly straightforward. You just need to integrate your question later carefully, okay? So please make sure that you don't do silly mistake lah. Okay, so exercise 1, given the velocity field of a body, so velocity is already given. So determine the spatial mass density in terms of initial density if the mass is conserved. Okay, so we have this relationship. So firstly, we need to find this. So del dot v. So you have del v1 plus del x1 over del x1, then del v2 del x2 plus del v3 del x3. So try to find these three. So you get a plus a, another a here, and then plus x3. There is no x3 here, so you get 0. So you end up with 2a. And then rewrite into this relationship. And then rearrange. So you get so here is ln rho equals negative 2 to 80 plus c, let's say. And then using the initial condition. So at time 0, rho is rho naught. So we get c. Okay, so c equals ln rho naught. Then rewrite rearrange. So you get okay, tambah space. I hope you understand how I get here. And then so rho is simply rho naught exponential of 280. Okay. So it's straightforward. You just need to calculate it carefully. Okay, so that's about conservation of mass. So conservation of mass will requires you to calculate the density and also the velocity. All right, so we move on to the second conservation law. So it's the balance of linear momentum. So the principle of balance of linear momentum, which is similar to Newton's second law of motion, or the set of particles stated as the time rate of change of linear momentum of a group of particles equals the net force exerted on that group of particles. So if you have force applied on a group of particles, then the rate of change of linear momentum of all of that particle will will be equals to that force. So this can be written generally as F equals dt ddt mv. So mv is momentum, or equals ma. So for deformable body, the balance of linear momentum can also be defined in spatial and material form. So let's look at the first balance of linear momentum in spatial description. So in spatial form, the rate of change of linear momentum within a system is equal to the sum of forces acting on that system. So the change in linear momentum equals the sum of forces acting on the surface of the body plus the sum of forces acting in the interior of the body. So you have many particles in that body. So you have to consider the external forces applied on that body, as well as the forces in between the particles. Okay, so there are two source of forces. So these forces will equals the rate of change of linear momentum. So ignore the derivation because it's quite not long, but susah nak faham jugalah. So the balance of linear momentum in Spartan description is simply this: rho times dv dt plus v dot gradient of v minus divergence of stress tensor minus rho f. So f here is the external force, and this is stress between the particles, and v is the velocity. Okay, so when we assume zero velocity or constant velocity, then the balance of linear momentum becomes this. So most of the time for solid mechanics, we assume the velocity as zero, okay? But in fluid mechanics, we have to consider the velocity for each particle because the particles of the fluid will constantly moving. So that's why if you doing CFD simulation, um, or if you do fluid mechanics, to calculate fluid mechanics or CFD manually is difficult because of this term here. And for continuum mechanics, for solid mechanics, it's a bit easier because we tend to assume this part here as zero, or we neglect these terms here. Okay, so if you this is just an extra information. So um, for fluid mechanics a problem, because there is this term here, velocity terms, that is very hard to solve. So we have to use numerical method to solve this part. So when we use numerical method, um, it is not as accurate as solving this equation manually. Okay, so for example, like in your finite element classes that you have taken, so finite element method is similar to numerical method, in which you solve this kind of equation by making some approximation. So it is not as accurate as solving this manually. So when you have a fluid mechanics problem because of this part, so there is a one mathematical prizes, in which if you manage to solve calculating this section or this solving this equation uh, sort of like manually, you can get $1 million. Okay, so if you are interested on solving this, or you if you want to win the prize, you can try. Okay, but many researchers have developed so many methods to solve this by not using numerical method, or maybe using some other mathematical ways instead of using software. So the problem still remains unsolved until today. So it's already many years, okay? But the price given started since 2000, the year 2000. So it's already 22 years. Nobody managed to solve and get the prize. So if you are interested, you can try it. I think there is a movie as well that explain about the fluid mechanics equation that is unsolvable, but I don't remember the movie. Okay, so let's look at an example. So let's say if you are given a Cauchy stress tensor. So let's say a Cauchy stress tensor of a body is given by this. So this is the Cauchy stress tensor, and the deformation map of that body is given by this. So determine the body forces so that the body is in equilibrium. Okay, so firstly, we determine the velocity and acceleration in spatial description. Okay, so we determine V1, V2, V3. Simply differentiate x1 over t, or x2 over t, and x3 over t, the small x. Similar to A1, A2, and A3. So A1, you differentiate V1, small v1 over t. But here, for V1 here, for example, you can convert it into a small x. Okay, but later when you want to find acceleration, you need to use the relationship with time that has time here. Okay, later on you can see this, how this is turns out as it is, and then you determine the del dot stress. So maybe we can rewrite the equation. So the equation is Okay, so this is the balance of linear momentum. So usually we ignore this part here. Okay, we still take the acceleration or the velocity rate of change of velocity. So after you calculate del dot stress, so this is the relationship for del dot stress. So you get a vector, okay, three values. So after you get all of this, the acceleration, the del dot stress, then you can substitute into this relationship here. So let's show this. So rho times, so del v del t is basically the acceleration. So you have x1, x2, and 0 minus del dot stress minus rho f. So we want to find the force. So force equals 1 over rho. So we have rho x1 minus 2x1. So you can factorize x1. And rho x2 minus 2x2 and 0. Okay, so similar to this one. Okay, so again, this is straightforward. So you just need to be careful when calculating del dot stress and calculating the velocity and acceleration. Okay, and when you want to find the force, just make sure you calculate it correctly. Okay, so exercise 2, I leave it to you to try it. So it's similar to the previous one. So, but in this case, there is no body forces, but you are going to determine some values for the constant or the condition for the constant when there is no forces. So basically del dot sigma equals 0. So how to determine the value of C1, C2, C3, and so on, simply using this. So here there is no velocity given as well. Okay, so you can try later. So just now it's the balance of linear momentum in spatial description. So in material description, it's having the same relationship. So the balance of linear momentum in material description is basically rho naught times material acceleration, material description of acceleration, minus del x big X dot P. So P is the first polar Kirchhoff stress tensor, and rho naught times F. So F is the force. So it's similar, but in material description. So again, exercise 3 is about using the balance of linear momentum in material description. So here you are given the displacement. So you are given displacement, meaning that you need to find the acceleration. Okay. So this is displacement in material description. Then you need to find acceleration, velocity, and so on. Okay. So try this and see how you can answer this. Okay. I didn't try because I don't know how to answer this. Okay, so we have covered two balance principles. So the third balance principle is the balance of angular momentum. So the balance of angular momentum states that the time rate of change of angular momentum of body is equals to the sum of moments acting on the body. So for rigid body, it's d dt I, moment of inertia, times angular velocity equals the summation of moment. Okay, so when we use this balance of angular momentum, so ignoring the derivation, so actually we obtain one of the important relationship, which is the stress, Cauchy stress is actually symmetric tensor. Okay, so Cauchy stress is a symmetric tensor. So meaning that, for example, Cauchy stress, if you have the Cauchy stress and this is the diagonal element. So let's say if you have A, B, C here, so the value below the diagonal element also equals the value on the upper triangle or the upper after the diagonal element. So when you have this kind of tensor or matrix, then the matrix or tensor is symmetric. Okay, so stress tensor is always symmetric, and if let's say you calculate stress tensor later, you get not symmetric answer, then you know that you are wrong. Okay, when you're calculating the stress tensor for Cauchy stress. So because of Cauchy stress is symmetric, that the second Piola-Kirchhoff stress tensor also symmetric. Okay, so the only non-symmetric is the first Piola. Okay, so first Piola are non-symmetric. So the Cauchy stress and second Piola-Kirchhoff stress are symmetric tensor. Okay, so that's it for balance of angular momentum. And lastly is the conservation of energy. So basically the principle of conservation of energy states that the time rate of change of total energy of a continuum body is equal to the sum of the work done by the surroundings on the body and also the heat added to the body. So this might include the kinetic energy, potential energy, but sometimes you can have other energies like thermal energy, electromechanical energy, chemical energy that may be involved in the conservation of energy. So there are a lot of different types of energy. So sometimes when we calculate, let's say, uh, we use kinetic and potential energy only, but we can also consider the heat energy produces from friction between the object and the surrounding. Okay, sometimes we neglect this because it is too small. Yes, so we have so many energy. So this different energy, when we calculate in this conservation of energy equation, will affect the overall, let's say, the particles displacement, the stress and strain. Okay, but how much the different energy affects the displacement and stress, that's the one that we need to discover. Okay, sometimes uh, like heat energy produced from friction is very small, so they can consider that as negligible. Okay, so as a summary, so what we have learned so far on continuum mechanics concerns primarily with the deformation behavior or the deformation gradient of a body under applied force. So to complete the mathematical description of the behavior of the body, the conservation equations or the laws derived in this chapter must be supplemented with constitutive equations. So we must have constitutive equations that relate F and the stress tensor. So in my previous lecture, most of the time when I give example relating F and stress tensor is simply an example, but the relationship is not actual. So in the following week, we are going to look at some constitutive equations that relate both F and stress tensor. So these constitutive equations um, actually describe the behavior of certain materials. Okay, So in the following lecture, in the next week lecture, we are going to cover two different kinds of material. We have linear elastic material. So basically linear elastic is stress uh, directly linearly change with strain, and we have non-linear elastic. So stress is a function of strain. Okay. So if you still remember this linear elastic, so we have Young modulus, okay, Young modulus, Poisson ratio, and so on. So this is the equation that you have learned maybe in SOM 1 and SOM 2. And for nonlinear elastic relationship is something like rubber material, or when the material exhibit plasticity. Okay? So if you still remember stress strain curve, so ada linear elastic, and then after that you ada yield stress lah, ada plasticity. Okay, so we are going to look at this uh, very briefly to look at the material constitutive relationship. Okay, so that's it for today's class. So see you again next week. So hopefully next week will be the last lecture, and then we will meet again on week 13 and 14 for talks from people that use continuum mechanics in their work, in their research. So thank you very much. Assalamualaikum and goodbye.
Doctor.